Welcome, everyone. My name is Fred Kim. I'm a product manager at the HBM Prenscia, in charge of the signal processing related tools we have at Prenscia. Today's webinar is about quantifying the reliability of automotive electronic components, and particularly when they're subjected to vibration. Before we start, just allow me to introduce HBM Prenscia and the range of tools we have. So basically, HBM Prenscia is a provider of tools and solutions to help engineers to optimize their reliability and the durability process. In terms of tools, we've got quite a large range, but this could be probably simplified like if you look at the left-hand side column, we've got all the reliability analysis tools, so system analysis, live data analysis, test design, etc. The middle column contains all the reliability management tools. So that's typically risk management and actions management, things like that. On the right-hand side now, we've got the nCode tools for reliability. And so we've got products for fatigue analysis or analysis of measured signals, either from a durability viewpoint or for vibration or acoustics viewpoint. The last one is Akira. That's a web portal where you can connect and get access to your data, to your processes with nice apps and things like that. There's a webinar coming up on Akira. So now, for the needs of this webinar, we'll only need a few of those tools. We'll mention them during the webinar. We'll use Weibull++, Alta, BlockSim, Lambda Predict, and on the nCode side, we'll use VibeSys for the vibration analysis and Design Life for the fatigue simulation. So what we're going to do during this presentation is first, we're going to introduce electronic components in cars, then how reliability is important, right, and the general principles that you need to adopt if you want to make sure your product is reliable. Then we'll have a closer look at a standard, and namely the ISO 16750 standard which is dedicated to the environmental conditions and testing for electrical and electronic equipment in road vehicles. Now, having introduced this standard, we'll see how beneficial it can be for you to use real measurements. So once we've got an environment that's well defined, we'll see how to demonstrate target reliability. And once we're there, we wonder, why can I not know the actual reliability level of my components? We'll end with some perspective, and I'll show you how to use FEA, finite element analysis simulation, to help designing your tests, and then a conclusion. So, we all drive cars, and we all know that our cars are full of electronic equipments. So, a typical modern car has tens of microprocessors. Those typically control the engine behavior, the safety, the comfort, entertaining system, all over the place. And this tendency of having more and more embedded electronic components is not will continue to grow, especially if you consider the autonomous cars that are coming up. So now, reliability is crucial, first for safety reasons, right, but also for obvious commercial reasons, we're talking branding here. We as customers are very demanding in terms of reliability. We want just things to work and not worry about that. So typically companies dealing or making sure that their components are reliable, companies able to demonstrate a given level of reliability are typically more successful because their customers will choose them rather than the company next door that doesn't care so much about reliability. So reliability is crucial. Now, when we have reliability, there are some general typical principles that are adopted, right? The main ones probably this path-tube curve. So here you've got the x-axis is time, and the y-axis, the vertical axis shows the failure rate. So typically at a very early age, you've got infant mortality. So that's due typically to manufacturing or defects in the product. On the other extreme, you've got wear out. So that's the end of life. So that's the material that's just, or the component that's just too old to function, right? In between, you've got what we call the useful life of the components, with typically a constant failure rate, and that's where our components have to work. So we want first the service life to be the warranty, if you prefer, to be in that regime here, hopefully before the end of life here, and we want this constant failure rate to be as low as possible. And in this very region, that's where typically we need to make sure that stress does not exceed strength, because that's what typically produces the failure. As we go towards the wear out, end of life, it's more fatigue mechanisms, whereby you've got variations of stresses. By stress, I mean environmental agents, could be temperature, but typically for fatigue analysis, material fatigue, it's rather mechanical stress, right? So the variation of stress, you get cycles, and as they are repeated, they start to create micro cracks, which will end up propagating and breaking the component. So we got those two failure modes typically. The stress strength. So you've got here a distribution of stress, and a distribution of the resistance of the material, and we're trying to avoid this region here where chances that the stress exceed the resistance are responsible for the failure. So that's one mode of failure. The other one is the fatigue one. But in both cases, you can measure first the distribution of the stress, and you can measure the resistance of your component, and that's key to assess the reliability of any component, basically. So now, if we focus on electronics, typically, the main reasons why a component fails is because maybe its housing, its package has failed, and therefore humidity or temperature, whatever, penetrates where it's not inside the component and next to the PCB, and like it's not expected to penetrate, so it's not meant for that case. The other common reason is the connection with the circuit outside the component. So typically we've got issues here, and the circuit board can also show failures. And typically those failures are due to defects in manufacturing, as we saw in the path-tube curve, right? That's the infant mortality typically. When it comes to external or environmental agents, we've got thermal stresses, mechanical stresses, chemical products, that can affect the reliability, get ultraviolet light, electromigration, etc., and often what precipitates a failure is the interaction of some of the agents that I just mentioned. Now here we're going to concentrate a lot on the mechanical stress in this presentation. And that's what this ISO standard is about. It's about the environmental conditions and testing for electrical and electronic equipment in road vehicles. And actually it's got 5 parts. For part 1 is general, second part is electrical loads, then mechanical loads, climatic loads, and chemical loads. So yes, we're going to concentrate right on the mechanical loads. So for those of you who are familiar with nCode tools, we've got a vibration database called Vibration Manager in nCode, more specifically in VibSys, where you've got the vibration profiles from various standards. You can add your own in-house vibration profiles. But here the good news is that we've implemented, in the upcoming release, we've implemented all the curves, all the vibration profiles coming from this standard 16750 part 3 mechanical loads. So you'll find a number of random and sine sweep type profiles. So these profiles are to be run at constant temperature or with a given temperature profile given in the standard. So I mentioned random vibration, I mentioned sine sweep, also known as harmonic vibration. Let's have a closer look at what those mean actually. So typically, road load data is can be typically considered as random signals. Random as opposed to deterministic. You can't predict what the mechanical load is going to be. Instead, it's some kind of random signal like that we typically represent as a PSD. Like you have to take into account that this random signal never repeats itself. It's every second is different, and a typical vehicle lifetime is for 4,000, 5,000 hours. So you can't afford to consider the time series here. So we represent that as a spectrum called the power spectral density. This ISO contains a number of those spectra, and the ISO standard typically requires the tester to run this for 22 hours per axis. Other vibration profiles are the harmonic profiles or sine sweep type profile. So it looks the same. It's a spectrum here, and basically some level at various frequencies, and it can be represented. Well, it represents, say, a signal like this one, mid-level amplitude at a growing frequency, and then at high frequency a higher amplitude, and then at very high frequency much lower amplitude, etc. That's how we represent typically with this spectrum a sine sweep. This is a vibration that components close to the engine will see, because typically the engine is the car's engine is a rotating machinery, isn't it? With shafts that rotate, and with imbalances, and the cylinders that are firing, etc., etc. All this making sinusoidal-like vibrations. So this ISO 16750 part 3 recommends quite a few sine sweep for components sitting close to the engine or close to the gearbox, and it gives not only the profiles but additional details such as the speed at which you need to go from one frequency to another. Then you've got a more complex vibration environment called the Sine On Random or swept Sine On Random. So that's typically for components experiencing vibration coming from both the road and so that's random, the random part, and from a rotating machinery such as the car's engine. That's the sine wave part. So the standard recommends that harmonic and random vibration be used in a mixed mode. That's the word that they use. So like simultaneously you play the random, and on top of which you run some run-ups and goes down. So that's Sine On Random. So all these are profiles that are given in this standard. Now, the standard also says in its introduction, be careful. This is just a best estimation. One can get up to the moment when results from measurements in the car are received, right? So those spectra, those profiles, do not replace car measurements, and we're gonna see now the benefits of having indeed real in service, in real conditions, real measurements. Another warning in the standard is the following: users of the ISO standard should not assume that a system or component that passes laboratory tests would also pass the field or fleet verification trials. So that's kind of that's telling me basically that if I follow this standard, like I pick one of those profiles for my component because it sits next to the engine or next to the wherever, I picked up the right profile, I run it for 22 hours, it passes the test. I'm not sure whether once it's installed on hundreds of thousands of vehicles, I'm not sure what the reliability will be. It doesn't mean it's 100% reliability. So also we'll also address this question of, like, how can I turn my vibration durability test into a reliability test in order to demonstrate a given reliability, and why not to find out what the reliability is of my components. So let's start with the benefits of having real measurements. So typically, those standards, there are many standards for various components, like this one is on electronic components and civil applications. Typically, those standards overestimate the level of vibrations, simply because they can't possibly cover all the different vehicle types with the different dynamics, the transmissions from the roads to the component, etc. They can't model the different engine, the different gearboxes. They can't cover all the possible road types, different continents, different country, have different road quantities, let alone the driving styles. Different users will drive the cars very, very differently, more or less severe, etc. So in order to cover all this, the spectra that are given are kind of envelopes. So I would say that's the main reason why you should do some real measurements, long-term and unattended measurements, tens, hundreds, thousands of kilometers, different users, different locations around the planet, if possible. The more you have, the best, statistically speaking, it'll be. And then what we can do inside of VIBESYS, we can compare the spectrum of the measured data with the spectrum given in the standard. And we can compare the severity in terms of fatigue, for instance, between those two sets of data. The main difference between the fatigue and the PSD is that the fatigue basically takes into account the duration. So it takes into account the fact that the spectrum from the standard is meant to be applied 22 hours, and it takes into account the fact that this noise may be only a few hours. So it's more comparable than a simple PSD overlay. So all this to say basically that as the manufacturer or the supplier of this electronic component, you may want to tailor a test such that it's fit for purpose, right? There's no need to exaggerate the test. And it's not mentioned on this slide, but there are cases where it's the opposite way around. Like the standard has not taken into account some extreme events, maybe, that you are likely to, or your customers are likely to encounter in real life. So sometimes you may as well find that the real measurements are a bit above what the spec the standard requires. So all this, you can do your test tailoring, and this is typically called within our product accelerated testing. So you may want to check out some webinars or documents or papers that we have on our website. So we've got now our spectrum. We have also possibly a temperature cyclic loading that we want to apply on top of the vibration profile. We've got a different a given duration for this test, and we can therefore run our shaker test. Now, right, the second question, the second warning or limitation of the standard comes now. Like, what insight does a successful test reveal about the ability for hundreds of thousands of components to survive their intended life? Is it because I passed this test 22 hours successfully that I've got 100% reliability on my components? All my 100,000 components will be successful within their warranty life or intended life? Well, let's see how we can do that. Basically, you want to answer one or the other of those two questions. The first one is, how many components should I test during 22 hours to demonstrate, for instance, 95% reliability, which goes along with a given confidence level. So say 95% reliability, with 95% confidence. So how many components should I test for 22 hours, right? And if none fail, then I know that I've demonstrated 95% reliability. That's a question you might ask, right? The other one, which is very similar, is how long should the test last, right? In order to demonstrate the given reliability based on so many components. So I put, say, 100 components on my test machine. I know the profile I want to use, both mechanical and climatic. How long should this test last in order for me to be able to demonstrate this level of reliability? So assuming those 22 hours represents the total vehicle, lifetime on vehicles, say 4,400 hours, assuming that the product's failure behavior is represented by an exponential low, right? You have to make some assumptions like that. Then you can calculate the number of samples or the test duration that are required to prove a given reliability level. So for instance, I used Weibull++ here it's got a module called test design, reliability test design, and say I want to demonstrate this 95 reliability, 95 confidence with my test duration of 24 hours. How many samples do I need? Turns out that I need at least 59 samples with no failures, right, after 22 hours of tests. This will demonstrate my R95C95 reliability level. Say now you've got only 50 components available that you can test. So the second example here is in order to demonstrate the same reliability level with only 50 samples, the test must last 26 hours instead of 22. With zero failure, if after 26 hours with no failure, then I can prove that I can demonstrate the R95% reliability. So this is just showing me that from the durability tests that I was planning on doing in order for me to be compliant with this ISO standard, by doing some very light extra analysis, I can also prove a given reliability level. Now the question could be, what is the actual reliability level? Because there's no point, or say, it's maybe not enough for you to demonstrate 95% reliability. You'd like to know maybe your 99% reliability or more, and you want to put this into light, right? You want to know about that. So what is the actual reliability level. So here what we can do is, again, we've got our test profile. We've got our samples that we put on the test machine, the shaker with the climatic chamber or what. And the idea is to test, to continue the tests until we've got enough failures observed. Like you want to have a number of failures, and then you can do your life analysis using Weibull++, and this will tell you the real reliability level. Now, if it lasts too long, because your components are very reliable, so it takes very long for the first failures to occur, you may want to increase the severity of the test. So increase either the mechanical load or the climatic load, or both, right, to precipitate the failures. And that's what we call quantitative accelerated life testing. And with the product Alta here, you can test your product at high stress, right? Find out all the reliability characteristics at this very high stress, and use some lows to infer the product's reliability at normal or use stress, right? Those lows, there's a number of lows that exist in the software. Depending on the failure mechanism, you will use another model to relate the reliability at high stress with reliability at normal stress. So using such an approach, you can very quickly determine what your reliability level is. Now, all this is fine if you are the supplier of A components to an automotive manufacturer. Now, your customer, the automotive manufacturer, has another problem. He's very happy that you are able to demonstrate a given reliability level, say, but as a manufacturer, he's a system integrator. Like the automotive is made of so many components, and the manufacturer, the OEM, is interested in the system's reliability. So his system is made of many components. So the idea is to combine the reliability information he's got or she's got for each component into a system to find the system's reliability characteristics. So that's done using BlockSim, the BlockSim package that we have. A few interesting facts is that here I represented just in series, different components in series to form a system, but those can be in parallel, not necessarily in series. It can be very complex. Can have hundreds of components in there. And the other interesting fact is that it's not dedicated to only electronic components. It can also incorporate mechanical components, like here you've got a PCB, the package, the bracket that supports the whole components, mechanical bracket, right, metallic or whatever, and each and every one of those has its own reliability, like on failure rates, on distribution, etc. So that's quite interesting for the system engineer to combine all this. Now, say this provider is the provider 1 is very good at giving you those information. Provider 2 is quite good as well. Provider 3, well, no information whatsoever about reliability. So you need to assess or to find out what like a reasonable reliability characteristics. So we've got Lambda Predicts that contains failure rates data for various electronic components, as you can see in the screenshot here. And those are coming from different standards, including the very famous MIL Handbook 217, or the French standard FIDES, or the communication telecom standard Telcordia, Belcor, etc., etc. So that gives you a first idea, or it enables you, doesn't hold you up. It enables you not to be held up, and continue your system analysis. Again, it's probably best to have field failure data, but that's a great help. Now, I mentioned mechanical components as well. I mentioned the bracket, for instance. That's very typical in lightweight vehicle, engineering. We typically we want to reduce the thicknesses of the various mechanical parts such that their weight is reduced, or we switch from metallic parts to plastic parts, right? So this can be modeled. The failure mode is typically fatigue for those mechanical components, brackets, etc. And this can be easily modeled using a finite element analysis and vibration fatigue analysis on top of that. So we've got a product called Design Life that enables you to do that. So you model your mechanical components, you load it with a given profile here, you give it some properties, and it finds at every single node what's the life and what's causing this life, like the mechanical stress level at that node. So this is very interesting. It's typically used in the world of testing. It's used to simulate the damage before even running the test. So you make sure your test that chances to be successful. Now, often what happens is if the test is not successful, you want to investigate why it has failed. Is it due to the material? Is it due to some resonance? Is it due to, so you may want to run simulations like that to better understand what has happened and therefore to take actions. Also, you can accelerate your test using such an analysis. You can compare different type of profiles coming from different standards, and that typically enables one to run one test instead of running a number of tests. Like you've got different customers, each one of them wants you to run a different profile. So what you can do here is make sure one profile covers the others, maybe in terms of fatigue damage or severity, generally speaking. So Design Life can be used to design smart tests, right? And I think that's it. I've reached my conclusion here. So what we said is that modern cars contain more and more electronic components, and reliability is crucial and will become even more crucial for many reasons, like safety, commercial, warranty-wise, legal reasons, etc. There are standards that provide you with environmental conditions, such as vibration profiles, for you to test those components, but there's nothing like measuring the real stresses that the product will be subjected during its life. Now we show that a durability test can be turned into a reliability test that demonstrates a target reliability level, or even if you continue it or make it more severe, you can find out what the actual reliability of the product is. And so once you have the reliability of one product, part of a system, you do the same with the other product, and eventually you can find the reliability of a whole system. And we saw also that finite element simulation, vibration, FE-based fatigue analysis, can help one optimize the mechanical parts of a system, make sure they are optimized in terms of weight, thickness, material, etc. So all this exists, or like HBM Prenscia, I showed you the tools we have, and we can help the engineer doing all this with the tools we have. So don't hesitate to contact us for additional information. You can